Dear colleagues, I am glad to present the latest part of our research named crack arrest simulation in steel in account of competing ductile and cleavage fracture. Large, welded Arctic structures like icebreakers, sea platforms, and wind turbines are being made of low alloyed steel having a feature of ductile to brittle transition. In other words, cleavage fracture at low climatic temperature may occur. This is why the safety of structure in service depends highly on the quality control system applied for the materials at the construction stage. In-service cracks usually start from welding floors and stress concentrators of welded joints. A resistance to crack start is provided by static fracture toughness measured in terms of CTOD&J integral. If a crack starts, it has to be arrested by base metal. This feature is described by a crack arrest temperature of base metal and the critical stress intensity factor K1A at this temperature. ESSO full-scale test as per ISO 20064 is now applied to find these values. ESSO test is now introduced into the shipbuilding rules. Researchers are now trying to find correlations of ESSO with small-scale ductile to brittle transition tests, because ESSO cannot be used in plant laboratories of steel manufacturers for prompt testing of industrial batches. In Russian practice of several decades, the following tests are applied: TKB, NDT, TKDS, DWTT, and so on. So the aim of this research is a suggestion of quantitative correlations of different ductile to brittle transition temperatures with the crack arrest temperature of particular steel determining the minimum safe design temperature of structures. A scheme of ESSO tests is a static tensile loading of 500 mm wide specimen to 2/3 of yield strength and cleavage crack initiation by drop weight. Leaving aside the huge equipment and cost, the following issues have to be noted. A crack path is not usually straight. The crack length taken for critical strength intensity factor calculation is a distance to the very crack tip, while the crack front is not straight. The applied stress is known before a crack start, but not at the moment of its arrest. A similar crack arrest test is performed in St. Petersburg Krylov State Research Center. A method of double tension is used to start a cleavage crack. The crack arrest temperature is related to a sharp change of fracturing stress. NDT is a wide-known needle ductility temperature by Filin as per ASTM E208. Specimen with a notched brittle deposit is loaded by a drop weight. We have simulated this test by finite element method and earlier suggested a correlation with full-scale test. TKB is a temperature corresponding to 70% shear portion and fracture of full thick static 3-point bend test specimens. The test procedure is given in the rules of the classification, construction, and equipment of mobile drilling units and offshore fixed platforms by Russian Maritime Register of Shipping. The first correlation of TKB versus crack arrest temperature was suggested by Danilov in 1991. The latest correlation applicable for modern low alloyed steel grades is presented here. This correlation is based on our analytical model of tunneling, crack propagation, and arrest verified by FEM simulation. We have introduced a dimensionless parameter of relative fracture toughness omega used in the energy balance equation of a tunneling crack. The elastic energy decrease at crack propagation is equal to the sum of increments of the work of cleavage fracture within the area of tunneling crack and of the work of deformation in subsurface zones of shear lips. The event of a crack arrest is associated with the rupture of shear lips on attainment of an average critical strain in subsurface areas. The simplified crack arrest condition has been formulated. This formula has been verified by FEM simulation of competing ductile and cleavage fracture with an application of criteria discussed below as applicable for TKDS test. TKDS test was introduced by B.A. Drozdovsky in early 1950s as a ductile brittle temperature evaluated at static 3-point bending of Vischer P specimens and corresponding to 1/3 load drop from the maximum load and about 70% share in fracture. The present research holds a discussion on simple criteria of ductile and cleavage fracture based on fracture mechanics and applicable for FEM simulation of test parameters like a shear portion and fracture and the load drop. Material is a low alloyed shipbuilding steel of the grade F40SW. A 3D quasi-static problem presents 1/4 of Vischer P's 3-point bend specimen. Uniform finite element mesh in the crack area has the dimensions 0.1 by 0.1 by 0.2 mm. The last figure relates to the direction along crack front. A critical stress referred to as cleavage fracture condition and a critical strain referred to as ductile fracture condition are applied. Loading is realized in the way of step-by-step displacement increase in direction normal to the crack plane. A crack extends at the expense of uncoupling the mesh nodes for which at least one fracture criterion is fulfilled. Displacement increase, continuation of loading, is only carried out when none of the fracture conditions are met after sequential nodes uncoupling. The first principal stress is considered to be normal to the crack plane, so the stimulation of fracture in the plane of symmetry is physically grounded. A pair of values, the uniform mesh size and the ratio He of the first primary stress to the stress intensity, allows to simulate the cleavage fracture condition corresponding to a certain stress intensity factor. A crack extension to a single mesh size related to the attainment of critical He just after continuation of loading, or to say displacement increase, is not ascribed to cleavage fracture because it is necessary to speed up the crack before talking about its arrest. Ductile fracture condition corresponds to the attainment of a critical strain intensity in any node ahead the crack tip in the plane of symmetry. The critical strain intensity may be found from the classical formula, including the initial strain of pores forming, a constant alpha proportional to the logarithm of the ratio of critical pore size to its initial value, and the hydrostatic stress component sigma m. As a certain value of alpha is not known, its effect was investigated at FEM simulation. Simulated fracture surfaces of specimens are presented. Black is cleavage, white is shear, notch area is not shown. Calibration of 3D problem in respect of stress intensity factor K1N A was performed by the solution of a plane strain problem for a wide plate. Small scale yield condition is observed with the same mesh size. Loading of the model was performed until the first attainment of the cleavage fracture condition. K1 for this plate is known from reference literature and is taken for K1A. Starting from He equal to 2.5, the load drop value corresponding to unstable crack extension is almost the same for different alpha, but the same He. It means that the cleavage condition may be related to the load drop. Unstable crack extension length and shear portion and fracture found from small-scale ductile brittle transition tests. So, the existence of correlation between crack arrest temperature and NDT, TKB, TKDS, and so on is proved. Different alpha value has no effect on cleavage fracture appearance. At the same time, the coefficient alpha appears to relate to the maximum load and the area below the load displacement curve, so both values here and alpha determine the required fracture energy. So, a shear portion in fracture or a load drop as a test criterion does not completely describe the fracture performance of material, but it is enough to describe the crack arrest behavior. This way, the crack arrest temperature can be assessed via TKDS. Further FEM simulation will be undertaken for materials of other strength levels to find a general correlation. Thank you for your kind attention. Email of the corresponding author is ctod@bk.ru.